Solving polynomial equations. Our objective, we want to solve. We want to find all the roots of polynomial equations that have integer coefficients. Now let's remind ourselves that roots and zeros are sometimes interchanged as we talk about them, but zero means you've touched the x-axis. And roots, you could have imaginary roots, which are roots that do not touch the x-axis. So roots is a bit more inclusive, speaking to zeros plus those that are not zeros, those that are imaginary. Hence we use the word roots here. Okay, we know a number of things that are going to come into play here. Let's briefly take a look at those. We know what a polynomial function is. A function of the form f of x equals coefficient times x to the n plus coefficient times x to the n minus 1, etc. until we get down to a constant. We know that if our powers are in order from least to greatest, it is in standard form. The coefficient of the term with the highest power is called the leading coefficient. So a sub n here is the leading coefficient. A sub 0 here is the constant term. We've learned about zero multiplicity. So if the graph of a polynomial crosses the x-axis, then that zero has odd multiplicity. If the graph of a polynomial touches the x-axis and turns around, that zero has even multiplicity. We know about synthetic division, kind of a shortcut when we're dividing by a linear term. A method to do polynomial division, again, that can only be used if the divisor is linear. It's in the form x minus c, and notice we have a minus c. So we need to make sure that we're dealing with c's that are following a minus operation. This is generally used for finding the zeros. Okay, again, roots include zeros of polynomials. We know the factor theorem. If c is a root, then x minus c is a factor. We know the rational zero theorem. If a polynomial has integer coefficients, then all possible rational zeros are found by listing all the factors of the constant term and dividing them by all the factors of the leading term. If there are rational zeros, they will be found in here, and again, focus on the integer coefficients. And of course, we know the quadratic formula from way back when. It's a formula, x equals negative b plus or minus the square root of b squared minus 4ac, all of that over 2a, and it can be used to solve any quadratic equation, and we tend to use it when we notice the quadratic is not factorable. Okay, so if these things have integer coefficients, these polynomials, we're going to start off using the graph to determine a possible rational root and thus a linear factor. We're going to be dealing, I believe our example is going to deal with a fourth degree polynomial, and the graph will help us take a look at that. Then we'll use synthetic division to determine a second factor, and then you kind of repeat this. Go back to the graph, okay, and see if you've got another rational zero, and then you can factor that one out using synthetic division, etc. Once you get down to the only remaining non-linear factor is a quadratic, then we know we use the quadratic formula or factoring. And then we can set each factor equal to 0 and solve. We're going to make use of the graph a fair amount here. It makes life a little easier. So let's take a look at an example. Let me flip this over and get us going here. Okay, example, we have a fourth degree polynomial. X to the fourth minus 6x cubed plus 22x squared minus 30x plus 13. And we want to find all of its roots. Again, as a reminder, some of its roots, all of its roots might be, all roots might be rational. they might be real numbers. They might all involve touching the x-axis or crossing the x-axis, or they might not. So we might have all of these roots are zeros, or we might have some roots that are zeros and other roots that are imaginary and that are simply roots because they don't touch the x-axis. So let's take a look at how this is going to go. Okay, let's take a look at the graph and see if we can find a 0. So go into my graphing device, go to y equals, and let's put it in. X to the 4th minus 6x cubed. Let's see, plus, I'm having to be careful here, 22x squared minus 30x plus 13. Let's hope we have a place on the graph where we have a real 0 or a rational 0 graph. Whoa, looks like my scale is pretty off. Let's go to my zoom. I'll let it finish graphing with this little circle spinning up here. Okay, let's go to zoom. Looks like I had a different window set. So here we go. Here comes the graph. I hope there it goes. Okay, it looks like I have a 0, and it looks like that 0 is at 1. Let's take a quick look here. Second, calculate the 0, and let's give it a left bound and a right bound to ask the calculator to look between these two bounds and press enter. And the 0 is indeed x equals, well, 0.999, that's just the calculator being finicky. There's a 0 at 1, we can see that here. Notice it touches and turns. So this 0 occurs 2 times, 4 times, 6 times. It's a 0 of even multiplicity because it touches it and turns. We're going to worry about it 1 time. So from the graph, okay, x equals 1 is a 0. And we mentioned even multiplicity. I'll come back to that in a minute. So x minus 1 is a factor. Again, it's even multiplicity, so we know it's a factor twice at least. Okay, 2 times or 4 times, but we're going to deal with it once here. So let's use our synthetic division. Let's pull the 1 out. And we have our coefficients of 1. We know it's a factor, so we know we should get a 0 remainder. So let's take our coefficients. We're already in standard form. I don't have any missing terms, any missing x terms. So 22, negative 30, and 13. We know we're going to deal with 3 rows. We're going to pull this down, and we're going to start our process. 1 times 1 is 1. Put it in column 2, add, get negative 5. 1 times negative 5 is negative 5. Put the answer in column 3, add, get 17. 1 times 17 is 17. Column 4, add, we get negative 13. 1 times negative 13 is negative 13. Add, we get 0. And we know this is our remainder. And we knew we had a remainder of 0 because we know that this is a factor. Okay, so now we know that x to the 4th minus 6x cubed plus 22x squared minus 30x plus 13 can be written as a product of 2 factors. X minus 1 is one of those factors. And the second factor, remember, this is our coefficients of our second factor, starting 1 degree lower. So it's x cubed, 1x cubed, minus 5x squared, plus 17x, minus 13. Okay? Now, we could go back and we could use our rational number, rational 0 theorem, but wait a second. And we know about that with these 3rd degree polynomials. We got to get this down so this is a quadratic. So we need to break this one down too. This one's done. We know that 1's a factor. We need to break this one down. Well, let's go back and let's remember what I said earlier. Okay, that this factor, the factor 1, is an even. It touches the graph at 1 and it turns around. So the factor 1 occurs a minimum of 2 times because it's an even here. Okay, so let's take it out again. Okay, so let's note that. At x equals 1, so we don't have to worry about the rational zero theorem, the rational zero theorem, because we know that this factor 1 occurs at least twice, so we can kind of avoid that. But you may need to use that. If it crossed it, you may have to use the rational zero theorem. So the graph touches and turns around. Okay, so x minus 1 is a factor of even, we know that from previous videos, multiplicity, hopefully spelled correctly. In other words, as we've said, x minus 1 is a factor, an even number of times, 2, 4, 6, is a factor at least twice. Okay? So this 1, make my equal sign a bit more clear here. This 1 is a factor at least twice. So I can take this result here and I can bring that down and take a 1 out of it. Because 1 is at least a factor 2 times. So now we can take the factor of 1 out of this using synthetic division. 1, negative 5, 17, negative 13. 1, negative 5, 17, negative 13. And again, we know this is going to be 3 rows. Let's bring the 1 down and let's start our process again, our synthetic division. 1 times 1 is 1. Write that number in column 2 and add negative 4. 1 times negative 4 is negative 4. Write the product in column 3 and add negative 13. 1 times negative 13. Oh, excuse me. Whoops, this is positive 13. Sorry, I bet you caught me and thought, what was I doing? 17 plus negative 4 is positive 13. 1 times positive 13 is positive 13 and add. And here's our remainder. We knew we had another 0. We knew that 1 was another 0 and it was a factor. So now I can say that x to the 4th, we're trying to break this thing down, minus 6x cubed plus 22x squared. I'm just writing the original right here. Minus 30x plus 13 is equal to, well, now I know that 1 is a factor twice, so x minus 1 is a 1 is a 0 twice, so x minus 1 is a factor twice, and then this is the quadratic I'm left with, which is x squared minus 4x plus 13. Okay? So now I've got it broken down. I had a 4th degree polynomial. I pulled out a linear factor. Whoops, I knew, let's go up to the top here. I had a 4th degree polynomial. I used my calculator to find a 0, which was 1. I factored it out using synthetic division, and I came up with a linear factor times a 3rd degree polynomial. I could have used my rational zero theorem on this, but I said, wait a second, I know something from the graph. I know that 1 is a factor at least twice. So I pulled it out again by dividing this result using synthetic division. And so now I've come up with a linear factor times a linear factor times a quadratic, and I know how to deal with a quadratic. Once I get to a quadratic, I know how to deal with that. So what do we know? We want to find the roots. So we're setting this equal to 0, And we know that this is x equals, this is x equals 1, and this is x equals 1. So I know that these are two of my roots. Now I've got to do this, okay? So we're going to use the quadratic formula because this is not factorable. So x is equal to negative b, that's positive 4 plus or minus square root. B squared is 16 minus 4 times a times c, all divided by 2 times a, which is 2 times 1. Okay, well this is equal to 4 plus or minus, what is 16 minus whatever the heck that is? I didn't do this ahead of time. Sorry about that. 16 minus 4 times 13. 4 times 13. That's a negative 36. That's the square root. Whoops, there's an imaginary number divided by 2. So this is 4 plus or minus 6i divided by 2, which is 2 plus or minus 3i. Okay, so we have two real roots, 1 and 1. It's 1 that occurs twice. And we have 2 imaginary roots, 2 plus 3i and 2 minus 3i. So solve it. Our solution set is, I'm going to write them all out. 1 comma 1 because it occurs twice. 2 plus 3i and 2 minus 3i. Now, of course, I wrote these down twice on purpose. Whoops, you can't see that. My apologies. I'm going to write, again, here's my work to get my 2 plus or minus 3i. So I wrote down the fact that this root occurs 2 times, and then 2 plus 3i and 2 minus 3i. Now officially, we have 3 different roots. Okay? But we want to note that this root of 1 occurs 2 times. So there's my solution set. A real root that occurs twice, and 2 imaginary roots. So now let's recap what this tells us. And I put this on another piece of paper because I wanted to leave plenty of room for that problem. What does this tell us? Okay, properties of roots of polynomial equations. Polynomial equations of degree n, have n roots. Okay, given that multiple roots are counted separately. So let's go back to here. Given that I counted the multiple roots of 1 separately, 1, 2, 3, 4. So, so a 4th degree polynomial will have 4 roots. Okay, again, given the multiple roots are counted separately. So in our example, we had 1 and 1. 1 occurred twice. And then we had 2 plus 3i and 2 minus 3i. Okay, so if you count the multiple roots separately, you will have the exact number of roots as the degree of the polynomial. And the second thing we want to note, if the imaginary number a plus 3i is a root, then the imaginary number a minus 3i is also a root. Imaginary roots, if we have them, always occur in conjugate pairs. Okay, so we want to keep that in mind too. As you work with this, using the graph really does help to use the graph to work to find the roots that the graph shows you until you work it down to a quadratic.